Hey everyone, welcome to the homework 3 walkthrough. So in this assignment, we're going to be having fun with divide and conquer, sorting, and medians. This basically covers everything that we've learned up to our Wednesday lecture earlier this week. The first assignment should essentially be a free 10 points. Really, all you have to do is follow this link to schedule a 10-minute conversation with me, so I can meet every single one of you in the class and get to know you a little bit better. We don't have to talk about career, about computer science, or anything like that. I just want to get to meet you, get to see your face, associate your name with a face, and then just get to know a little bit about, what brings you to NCAT, what brings you to Greensboro, what are your plans after college, stuff like that. Also, when you're done with the homework, please complete this form. This is a Google form that is currently open. It will essentially ask you a few questions about how long it took you to do the homework and how difficult it was. This really helps me in figuring out how I can modify the homework to make sure that you guys are learning the material while at the same time taking into account that not everybody has a lot of time every week to work on this. Cool. So let's actually get started. The first real exercise is called this first exercise, the faster merge sort. So what you want to do here is you are presented with a modified version of merge sort. This algorithm, basically what it does is first it calculates the size of the input, and if the input is of size 1 or smaller, it immediately returns it. So again, this is our, for example, our base case. This is not different from the normal merge sort. Then you can see that the next couple of lines here, essentially what they are tasked with doing. Let me make this screen a little bigger so you can see. We create an empty vector called sorted subvectors. And what we do is we iterate over our input. So we start with I equals 0 to I equals 1. And we call ourselves, merge sort n is the name of our function. So we call ourselves recursively on a much smaller version of the input. This version of the input is essentially looking at from the ith index up to the ith plus 1 index. So what we're doing here is if we have an input, zoom in here, if we have an input that is 1, 5, 8, 10, what this for loop is doing is it's essentially calling merge sort n on 1. It is then calling it on 4. It is calling it on 8. And then it is then calling it on 10. So it basically calls it in each of these set vectors, and then whatever the result is, this temporary, gets pushed back into these sorted subvectors. So at the end of this for loop, sorted subvectors is going to look something like this. It's going to be a vector of vectors that have 1, 4, 8, 10. So hopefully that's clear to you. Then what it does is it iterates over each of these subvectors. So we're going to be pulling each of these out. And what it's going to do is it's called our merge operation on this sorted A, which starts out as empty, and the subvector that we're pulling out. So walking through this example, sorted A is going to start as empty. After the first iteration of the for loop, it's going to call merge on sorted A and this first subvector, which is 1. So after the first iteration, this is going to be just the vector 1. After the second iteration, sorted A is now going to have 1 element in it, and we're going to call it with this sorted vector 4. So it's going to merge the two, and it's going to create sorted A as 1, 4. You can continue that way after the, on the third iteration, sorted A is going to be 1, 4, and subvector here is going to be this vector 8. So it's going to merge them. So again, it will give you 1, 4, 8. And then similarly, after the final iteration, sorted A is going to be this vector 1, 4, 8, and it's going to call it on this subvector 10. And it will return 1, 4, 8, 10. This is probably a bad example because these are already sorted, but let's say we had started like this. 1, 8, 10, 4. Then this would be 1, 8, 10, 4. And then this would be 1, 1, 8, because 8 is bigger than 1. Then we insert the 10, so it would be 1, 8, 10. And then we insert the 4, and actually when we call merge, it will take this vector, since this vector is sorted, it will correctly insert the 4 into the position where it belongs, which would be here. So as you can see, this does in fact return a sorted version of our vector. So essentially what we just covered is, in your own words, you want to describe what the above algorithm is doing. This is the answer to 2.1. So take a look at the code again and what we just discussed, and do your best to describe in your own words what the algorithm does. Question 2.2 is asking how fast the algorithm is. So essentially we have this argument that tries to provide a big O running time for this algorithm. Let me erase this. The argument is that first merge sort splits the array into n subproblems of size O of 1. So this is true. It first splits the array into subproblems of size 1 each. This is exactly what sorted vectors is, and when we called ourselves recursively, we called ourselves on input of size 1. So that's a perfectly valid argument. It does mention we don't waste time doing log n levels worth of splitting. Again, this is true. We only call ourselves n times, but we will no longer recursively call ourselves. When we make this call to merge sort n, there will be no future recursive calls because this already has an input of size 1. So again, this is also true. Then it mentions that we're calling merge on a bunch of subvectors of size 1. Therefore, each merge will take O of 1 plus O of 1 equals O of 1 time. So this is actually where you might already notice an issue with this proof. As we saw in the later parts, we are calling ourselves on an empty vector. So this is merge, we call merge sorted A and then subvector. The first time we call it on empty and 1. The second time we call it on 1 and 8. The third time we called it on 1, 8 and 10. And you can see that sorted, we're not always calling merge on vectors of the same size. So that already hints that this analysis is wrong. And that is exactly what we're expecting for your thought process here, which is an explanation, one sentence, that summarizes the mistake in this analysis and also provides the correct running time for merge sort. So one way to try to think about the correct running time is all of the analysis at the beginning was perfectly correct. So calling ourselves merge sort on these smaller arrays, this takes O of n time because we end up having n smaller arrays. These sorted subvectors don't really matter, so I'm going to delete that. Really, the rest of the running time is going to be on our calls to merge. So do remember that merge has a running time O of k, where k is the size of the largest, is the sum of the two input vectors. So what we do know is that we're always calling merge on some vector whose size is increasing by 1 each time. And then we call merge on the second parameter is going to always be of size 1. So the first call to merge, here, where we call it on empty and 1, this is going to take O of 1 time. That is correct. However, what I want you to think about is how much time does the last call to merge, take? So the last call to merge will be called on a vector sorted. It'll be merge A, B, and the size of A is going to be n minus 1, and the size of B is going to be 1. So the running time for this call is going to be O of n. Now, this is for the last call and for the first call, but do note that we call merge n times. So essentially O of n. So our outer for loop is called O of n times. And within the for loop, at the beginning we do constant work, but at the end we do linear work. One way to try to think about this is to suppose we, again, big O is an upper bound. So ignore the first half of the work. So for the first half of the array, for the first half of the for loop, let's say we call ourselves n over 2 times. And each time, let's say, we happen to do constant work. Let's ignore this. Okay. What about the second half of the for loop? So again, we're going to call ourselves n over 2 times. Not call ourselves. We're going to iterate n over 2 times. And each time, we're going to call merge on two vectors, a, b. And what do we know about a? We know that a is at least n over 2 in size. So that should hopefully be enough information to you to figure out the correct running time. Cool. Moving on to the rest. Question 3 asks you to find the matching elements. So first, the first thing to understand here is essentially the problem statement itself. So what's going to happen is you're going to be given an array of n integers that are sorted in ascending order. So what does this mean? This means that you're going to be given a sorted array, something like this. 4, 5, 6, 7, 8, let's say, for example. And you know that a1 is less than a2, which is less than ... a n sub 1, which is less than a sub n. So what this also tells you is that each of these elements are unique. There are no duplicates because they are all strictly less than each other and they're sorted. Okay. Now, his project is to search the above array and find an element such that its index is equal to its value, or returns that such I does not exist. So what does this mean? So what we can do mentally is this is our array A. We can think, what is the index of 1? Well, the index is 0. So let's say these are my indices. Index is 0. The index of 2 is 1. The index of 3 is 2. The index of 4 is 3. The index of 5 is 4. Index of 6 is 5, and so on. So for this problem, there is no place where the index actually matches the value of the element itself. So in this case, his algorithm should return that there is no I where I is equal to the value. Basically where I is equal to A of I. However, you can imagine you can easily tweak this. Let's say where this is 0, 7, etc. You could imagine that this is -1, this is 1, and then this is 3, 4, 5, 6, 7. And then in that case, you'll notice that the index of 1 is 1. So you would, in this second example, you would return, your algorithm should return, if I run it here, let's say find matching. If I run it with the array A, that should return 1, which is the index of the element and the element itself as well, right? You can imagine that this might not be true. Maybe this is 0, and maybe this is 3. This is 1, and this is 3. So in this case, we see that 0 does not match. The value at index 0 does not match its index. The value at index 1 does not match its index. The value at index 2 does not match its index, but the value at index 3 is actually equal to 3. So it does match its index, in which case now we would want find matching to return 3. So that's the problem statement, and that's what you have. So for the first part, Caleb actually gives you pseudocode for an algorithm that tries to solve this problem. And essentially what I want you to do is to understand the pseudocode and describe in a few sentences how it works. And also, it does work. It is actually a correct implementation. It does work. So I want you to describe how it works, as well as provide the running time in big O of this algorithm. This shouldn't be too challenging, I hope. 3.2 is the slightly more challenging part. So something to notice is that Caleb's algorithm does not actually take advantage of the fact that the array is sorted. So knowing that the array is sorted, there is actually a log n algorithm that solves the same problem. So you can take advantage of the fact that A is sorted. And what I want you to do here is I want you to provide pseudocode for the algorithm. So it'll be similar to what is written here. It does not have to be valid C++ code. It just has to be precise. It needs to talk about every step that your algorithm takes. And I need to explain in English why your algorithm works. You do not need to prove why it works, but you do need to provide an explanation as to why your algorithm works. One way to think about this is that you might want to, you guys should be familiar with binary search. I believe this was covered in Comp 280, and you've probably seen it in other CS classes, but you would want to do a modified version of binary search, which essentially means, what you would want to do, again, you see that the running time is log n, so that immediately tells you that you probably need to split the array into parts that are smaller. Normally, you would split it into halves. So the first thing you would do is you might say something like, create a base case. If my length of A is 1, then what do I return? If I have an array that is by itself with just a number, do I know whether this number matches its index? How can I know? Well, I know the index is 0. So I can check if A of 0 equals 0. If that's true, then I return 0 because that is the matching index. If that's not true, then I throw an error. No matching index. So this is the example of a base case here. Now, the next thing, like I mentioned, intuitively you should be thinking about splitting this array into pieces. So again, I gave you a hint that this might be related to binary search. So again, because the array is sorted, we can just try out that approach and see where it takes us. So normally in binary search, you would say something like, look at the middle element. Okay. So how do we write that in pseudocode? We say, okay, middle index is n divided by 2. Whatever. We don't need to worry about the +1, -1. This is pseudocode. We're just trying to give the general idea. And then we're going to say the middle is equal to A of n divided by 2. Now, in binary search, now you have essentially 3 cases that you want to consider. Usually you do a comparison. Okay. So let's think about this. There is a scenario where you get really lucky. What is that scenario? I want you to pause the video and think about that. The scenario where you get really lucky is actually where the middle index is actually equal to the middle value. Why? Because if this is true, then you have now found an I. So for example, here, let's say 0, 1, 2, 3. Let's make this array 1 shorter. So you'll notice that our array is of size 7, which means our middle value is going to be 3. And what's going to happen here is we're going to notice that our middle index is 3 and our middle value is 3. So we can actually immediately return the middle index. We're done. Now, the other 2 cases you want to consider is if middle index is bigger than middle and if middle index is less than middle. Does that help you throw away one part of the array so that you can call yourself recursively? Again, you probably want to pause the video and think about this for a little bit before we move on to the next part. What I would say is you can actually look at these examples. So suppose the middle index is bigger than the middle. So again, let's go back to our example here. Let's make something where the middle index here is bigger than the middle. So let's say this is 2. So the middle index is 3, and it's going to be bigger than the middle. Okay? So immediately, what that should tell you is this, you know what the index, what this list is, right? This is 0, 1, 2, 3. Those are the indices. Now, you know that this value is smaller than 3. What do you know about this value? You know it's a 1, but you know that it must be smaller than the value to its right. Therefore, this value must be less than 2, which means it cannot be, it must be less than whatever this number is, which must be less than whatever this number is, which is 3 in this case, which means this number cannot possibly match its index. By similar logic, if this number is smaller than its index, this number must be smaller than its index. Then when you look at the number to the left, you will realize, oh, this number cannot possibly match its index. This number cannot, the only way it would match its index is if this number is 1, but it cannot be 1 because it must be smaller than the number to the right. Again, all the numbers are unique and they're sorted. Therefore, if your middle index is bigger than the value, you know that you cannot have a match on the left side of the array. Okay, so that intuitively, that tells you that you want to call yourself my algorithm, you want to call yourself on the right side of the array in this case. So you would say something like, let's say our array is A, and we would call ourselves on n divided by 2 onwards. So we would call ourselves on the right side of the array, and we know the middle element doesn't match, so we might even call ourselves on everything except the middle element. So we go over by 1, and we look at the right side of the array. Now, this is not complete. What is this going to return? This is going to return an index in our smaller array that matches the value of the array, right? So this implementation is actually not fully correct. You want to do something in order to modify this implementation, right? Which is we are no longer looking for the index that matches, because we've made our array smaller. What that means is that now the indices are going to look like this. You're going to have A is equal to 4, 6, 7. And you're actually going to have your indices now are going to be 0, 1, 2. So you are not going to get a match here, which means you need to do something. You need to pass around extra information in your implementation so that you know that now you are trying to find not the index that matches, not the value that matches its index, but the value that matches its index plus 4. Okay, so I'll leave it as that. Matches plus 4. And you can follow similar logic for the second part, except it's actually a little bit easier. So this is tricky. It's tricky because you need to change the index you're looking for. And then in the second part, you can actually just call your algorithm on the first half of the array by similar logic to the above. So you can just call yourself on the first half of the array, and you will not need to modify what your algorithm is doing, because if we call ourselves on the first half of the array, you will have -1, 0, 1. And your indices will be still 0, 0, 1, 2. Okay, so definitely think about that. I would say one thing that you want to consider is you might want to consider your algorithm to, instead of being algorithm and just take A as an input, consider taking A as well as an offset, which is how much to offset the index you're looking for by. And that will actually help you solve this problem and handle the case here where you are returning the wrong index. Okay. Moving on to the next one. For problem 4, we actually have, you're going to be given 2 arrays, each of length n. So the arrays are going to be the same length. So 2 arrays of length n. And your goal is to find the median of all the elements. So in the first one, I'm asking for an algorithm that is theta of n log n. So that means it runs in exactly n log n. If you see an n log n running time in your head, you should probably think, pause the video, you should probably think merge sort. All I want you to do is to give me a short English description as well as the pseudocode. So again, your pseudocode might be something like find median, input 2 arrays A, B, each of size n, unsorted. Output, the median of all elements in A, B. Now, since you saw that the running time could be n log n, a very trivial implementation here might be to merge sort the combination of A plus B. So step one is maybe combine the arrays A and B. So this is pseudocode. You don't have to explain how this works, but let's imagine that we can just combine them again. This would take, combining arrays should take O of n time. There's nothing complicated about it. Then we sort our combined. So that's sorted. And then we return the median, which in this case would be sorted of n. Why I said n? Because it's sorted of the size of the array, which is going to be n plus n, because each array is of size n. So when you combine them, it'll be of size n plus n divided by 2. But this is just n. So you would return sorted. For the second part, you're also given unsorted arrays, but now you're asked to provide an algorithm that runs in linear time. And I do give you a hint here, which is you can use select AK from class. And we know, so you would have similar pseudocode, but now we know that select, C of K runs in O of n time. So again, this is not meant to be a trick question. You should immediately be able to select the median of the larger array, even if they're unsorted. Now, for part 4.3, this is a more challenging question. I won't give as many hints for this one, but it is asking you to find the median of two sorted arrays. Okay, so now your pseudocode is going to look a little different because you have two arrays, A, B, each of size n, that are sorted. So your arrays are sorted. And what you want to do is you want to find the median of those two arrays, and you want to find it in an algorithm that's O of log n. Again, when you see log n, you should probably think something along the lines of, I'm going to use divide and conquer. So I'm going to need to somehow split my arrays into pieces that help me figure out the left and like which way to recurse such that the problem gets smaller. Pause the video, think about that for a little bit, see if you come up with an idea. I do give a couple of hints, but generally speaking, the pseudocode is not too difficult. First, you want to consider the base cases. Let's cover those for completeness. So again, there are a couple of interesting base cases, which is going to be if A n minus 1 is smaller than B0. So what does this mean? This means that the biggest element in A, remember the arrays are sorted, the biggest element in A is smaller than the smallest element in B. Then that actually means that all of n is small, all of A is smaller than all of B. But A is of size n, and B is of size n. So actually the median, you can immediately know what the median is. The median is going to be A n minus 1. It could also, you can also validly, I don't really care about the details here, you can also return B0. Either one is correct. Let's say the median is the middle element if it's odd, and if the arrays are even, it is either the one before or the one after, whichever one you want to return. You can also take the average and divide by, take the average of the two elements and return that. That would work just as well. This base case also gives you another base case you might think about, which is what if B n minus 1 is less than A0? So again, this is saying the largest element in B is smaller than the, and you can actually make this be less than or equal to, is smaller than the smallest element in A. So again, what this means is that all of B is smaller than all of A, which again gives you immediately, you can return, let's say, A0 as the answer for this one. So you have two base cases already where you can immediately figure out what the median is. There's another base case where you can immediately figure out the median. but it's going to require a few more hints. So the hint I will give you is look at the medians of A and B. Okay, so let's zoom out a little bit so we can keep coding. Pause the video, think about that. What I would recommend is median A. Let's call it median A and median B. So these are going to be equal to A n divided by 2 and B n divided by 2. So again, these are the medians of each of the two arrays that I'm looking at, correct? Now, we have two numbers, so we can consider three cases. Either median A is going to equal median B, or median A is going to be smaller than median B, or median B is going to be smaller than median A. So in this case where the medians are equal, what does that tell you? Think about that. What you're saying is that your array A is equal to some numbers and then median A and then some numbers, where this half is exactly half of A and this is half of B. And now you're saying your array B is equal to some numbers, median B, and then some numbers, where this half is exactly equal to the size of this, because that's what it means to be the median, is that it splits your arrays in half and the arrays are sorted. Now, another thing you know is that both A and B are the same size, right? So you actually know that this half is the same size as this half, which is the same size as this half, which is the same size as this half, okay? So this is the situation we're in. And we're considering, what if median A is equal to median B? Then what do we know? Let's call this half A1, call this half A2, call this half B2, and call this half B1. So what we know is that half A1, all of these elements, of which there are how many? N over 4, are smaller than median A. And they're also smaller than median B. Now we also know that these half B1 elements are smaller than median B, which means they're also smaller than median A. So they're somewhere here. So we don't know how they combine, like they could be intermixed, but we know that half B1, which is size n over 4, we know all of these elements have to be smaller than our medians. But wait, if this is n over 4 and this is n over 4, this is half, this is n over 2, this is n over 2. This is half, added together, that's n elements that are smaller than median A equal median B. So then that means that median A and median B, that is the median of the whole array. So we can immediately return either one, median A or median B, they're the same. So you want to think through similar logic for each of these, which essentially should help you throw away parts of A and parts of B. So you can then call yourself recursively on find median of a smaller version of A and a smaller version of B. And then similarly, for the case where median of B is smaller than median of A, you want to call yourself recursively on smaller versions of each of the arrays. It's going to turn out that each time you call yourself, you're going to essentially take halves of each array as your new arrays. So the running time of this algorithm, we can actually write the recurrence, is going to be t of 2n is equal to t of n, because we are going to end up calling ourselves only once, and we're going to do constant work each time we call ourselves. This is the same as t of s is equal to t of n divided by 2 plus O of 1. If we say, s divided by 2, if we say s equals to 2n, we can let s equal 2n, which means n equals s divided by 2. And this recurrence relation, you can actually use the master theorem to figure out the closed form running time. Obviously, I did also give you the running time in the problem. So all you need to do is give an explanation as to why the running time is the way it is, which essentially means give this recurrence relation. Cool. Exercise 5 is actually my favorite. So we're going to spend a little bit of time on that one. Hopefully everything else so far has made sense to you guys. Exercise 5 essentially introduces two new concepts, a Las Vegas algorithm. So a Las Vegas algorithm, they're both random algorithms, but a Las Vegas algorithm is an algorithm that is always correct. So it always gives you the right answer. Quick sort, BOGO sort, the select algorithm, all algorithms we have covered in the class so far are Las Vegas algorithms. They always give you the right answer, but the running time might change depending on how lucky or unlucky you get. So all of the algorithms we've covered in class so far are Las Vegas algorithms. There are also something called Monte Carlo algorithms, which is essentially the opposite. The running time is fixed, okay? So the algorithm will always take the same amount of time to run, no matter, the running time is not going to depend on whether you get lucky or not. It will always be the same, but you might get a wrong answer from the algorithm. That's a Monte Carlo algorithm. So to summarize, Las Vegas is always right, but running time depends on luck. And Monte Carlo is always, we know the running time, but answer could be wrong, or answer depends on luck, like how lucky we get. These are the two versions of the algorithms we're going to cover. And basically, what we're going to be looking here is there's a problem called find majority element. You're actually going to implement it as part of your coding assignment, so that's going to be pretty exciting. But finding the majority element is essentially you are going to be given a vector. For example, this vector here, 2, 2, 2, 2, 2, 3, 5. You are given a vector where it is guaranteed that one of the elements occurs at least n divided by 2 times. Okay, so it will be the strict majority. So in this case, 2 occurs 1, 2, 3, 4 times, which is bigger than 6 divided by 2 is equal to 3, right? So the problem is, given this array, give me the element that is the majority element. So give me the element that occurs more than n over 2 times. Now you are guaranteed that you will always be given an array where the majority element exists. So you actually don't have to worry about the case where the majority element doesn't exist, at least for this problem. Cool. And what we're doing is you're going to fill in this table. So that means you're going to put in yes or no on the first column. You're going to put in the big O expected running time in the second column. You're going to put the big O worst case running time in the second column. And then you're going to put in the probability of returning the majority element in this fourth column. So something to keep in mind again, if your algorithm is Las Vegas, then it is always correct. So probability of returning the majority element is 1. So that's actually kind of free. If you can tell whether it's a Las Vegas or if it's Las Vegas, if you put Las Vegas in this first column, then you will put a 1 in this last column. Okay. So now these 3 algorithms actually refer to the next page. So here we have 3 different pseudocode algorithms for finding the majority element. Okay. Then we also have this algorithm number 4, which is actually not a random algorithm. This algorithm is deterministic, and all it does is it checks to see if an element is the majority. Okay, so given a vector p of n elements and an element small p, it tells you true if p is the majority of it is the majority element in the vector. So again, for example, if I did is majority 2, this should return true. because 2 is the majority element. If I did is majority 3, this will return false because it is not the majority element. Now, the implementation is given to you. So again, you just need to understand what it's doing to figure out the running time. So here what we do is we iterate over, so this is saying for Q in P, so for each element in my array, if P is equal to Q, so if the majority element you told me might be the majority is equal to Q, then I'm gonna increment the count by 1. Then if the count is bigger than n over 2, I will return true, otherwise I'll return false. So this for loop is gonna take O of n time, which means is majority takes O of n time. So this is going to be helpful because is majority is used in all of these other algorithms. But now we know that it takes O of n time. It is not random. Is majority is not a random algorithm. It is algorithm 1, algorithm 2, and algorithm 3 are the ones that are random. And for each of them, you want to figure out the expected running time, the worst case running time, and whether it's Monte Carlo or Las Vegas, as well as the probability of returning the majority element. Again, if it is Las Vegas, the probability of returning the majority element is 1. So let's take a look at each algorithm. I encourage you to pause the video before following along. I will be giving quite a few hints. So the first algorithm, what does it do? It has a while loop. So it says while true. So that means it's going to keep running forever until it returns. I will choose a random element from my vectors. So I will pick some number here at random. And that by random here, we mean uniformly at random. If that element is the majority, then I return it. Otherwise, I keep going. I try again. So is it Las Vegas or Monte Carlo? Again, Las Vegas always gives you the right answer if it returns. If it returns, it will always be right. But the amount of time it takes to run depends on how lucky you get. For Monte Carlo, the amount of time it runs is given. You know ahead of time, given the input, how long it's going to take to run, but it might not give you the right answer. So I want you to, for this one, you probably want to answer, is it Las Vegas or Monte Carlo? Again, if it's Las Vegas, then probability that it finds that the probability of getting the right answer is 1. So we would be able to fill in probability of returning a majority element would be 1. Okay. The next thing is we want to figure out the expected running time and the worst case running time. So again, on Wednesday, we covered this in Wednesday lecture. The expected running time is the amount of time you expect the algorithm to take on the worst possible input, but where you are making random choices. Okay? So for this case, really the running time is basically going to be, one question is how many times, essentially the running time is going to be number of times while loop runs times the running time of is majority, which is O of n. Because we can assume that choosing a random element is going to be constant time, so we're going to ignore that. But running is majority, we said, is O of n. So all we need to answer is how many times do we expect the while loop to run? How many times do we think it's going to run? And one thing to consider there is that you should notice that this is essentially proportional to the probability, or inversely proportional to the probability of finding the majority element at random. Does that make sense? So again, probability that if I pick a random element, that element is the majority. What is that probability? Well, I know that the majority element must be at least half of the array. Otherwise, it wouldn't be the majority. So actually, the probability that I pick it is at least 1/2. Could be bigger, right? So again, now you can think of this as flipping a coin. if half of the time I'm right, so I get heads, and half of the time I'm wrong, I get tails, how many times do I have to flip a coin before I expect to see at least one heads? Okay. Again, we covered this in Wednesday lecture, but the answer here would be expect to flip twice, because half of the time you will get a head. So if you flip it 2 times, you expect to get at least one head. Again, you might not, you might get unlucky, but in expectation, you'll only need to flip it twice in order to get a head, which in this case means in order to randomly pick the majority element. So the number of times the while loop runs in expectation is 2, and each time it runs, it takes O of n time. So the expected running time, you should be able to figure out exactly what it is. Now the worst case running time is when, let me delete a little bit of this. The worst case running time is when your algorithm, when somebody else controls the randomness in your algorithm. So the worst case running time is you get completely unlucky. You are the unluckiest person to have ever existed. The random selection never goes according to plan. So in this case, I feel like maybe take a look at BOGO sort from lecture. That should give you a hint. Cool. For the second element, again, you want to do a similar analysis. I think here one thing to notice is that this for loop is very similar to this while loop, but we only ever run it 100 times. So it has a fixed number of times it runs. Okay? So that should tell you, for example, that we won't always return the right answer, because we might get really unlucky where we try it 100 times, but we never pick the majority element. And then we actually just return the first element in the array. Okay? So this is an interesting algorithm to consider. The third algorithm here is first you shuffle your elements in P, and then you iterate over each element in P, and if it is the majority, then you return it. Mm-hmm. So again, this algorithm always returns the right answer. Why? Because we iterate over every single element in P. So for every element, we ask, are you the majority? If you're the majority, then we return. If you're not the majority, then we don't return. Okay? So this algorithm always returns the right answer, but the running time is going to be interesting, because since we shuffle the array at the beginning, how many elements do we have to look at in expectation? You know, how many times will this for loop run in expectation before I return? So the expected running time is going to be interesting, because in expectation, this for loop is actually not going to look at every single element. It'll be very similar analysis to what we did here when we chose a random P, right? Because the majority element occurs more than half of the time. So if you shuffle the array randomly, what's the probability that it's the first element? What's the probability that it's the second element, right? So in expectation, this for loop does not run n times. It actually runs something similar to how many times this while loop runs, okay? Which means in expectation, the running time of this algorithm will be how many ever times this for loop runs times O of n, which is how long it takes to check if an element is the majority. Now, in the worst case, we can actually think about the worst case. If we get really, really unlucky with the way we shuffle our elements, then we might actually have to run this for loop for n divided by 2 times. So if we get so unlucky that all of our majority elements are at the end of the array after we shuffle them, then we will check all the first n over 2 elements, and none of them are going to be the majority. So in the worst case, in the worst possible case, we will run the for loop n over 2 times, and each time we run it, n over 2 times, and each time we run it, we will take O of n time. So that should give you an idea for the worst possible running time. All right, let's jump to the coding now. So again, the coding is available on Replit. So you can just pull it up here. A few of you are already working on this. So I'll pull it up. This is what the coding is asking you to do. You have two problems, find most common and find peak. So again, find most common is actually the algorithm we just covered in part 5. Again, I want you to implement an algorithm that is always right. So it needs to always return the right answer. I don't care if you use randomness, that's okay. But it must always return the right answer. And you actually have a choice of algorithms. You can think of your own, but in the homework assignment, you, as we discussed, algorithm 3 and algorithm 1 will always return the right answer. So again, I don't care about the running time, so you can implement either of these two algorithms. Or you can just implement the easiest algorithm you can probably think of, which is, if we have, let's go here, go to answers. I would encourage you to pause. It will find most common for vector. Again, you can assume that a most common element will exist, okay? You can always assume that. I will only give you vectors where a most common element exists. So you don't have to worry about the case of like, oh, what if I have 1, 2, 3? And which one is the most common? I will never give you that as input. You can assume a most common element will exist. So the most trivial way to do this would be to essentially for element in vec. So for each element, let's see if it's the most common. So for other in vec. Let's count for each element. Let's count how many times it occurs. So for each element in the vector, how many times does it occur? So that means if element equals other. So if they're equal, then I increment my count. Now, once I'm done with this for loop, I can just check. Are you the majority? Did you occur vec that size divided by 2 times or more? If you did, then I'm done. I return that element. If you did not, then, I'll throw invalid argument. We should never get here because I will never give you an array that does not have a majority. Should not get here. So that's the simplest implementation. I do encourage you to try to do an implementation that's more interesting. You can try to implement any of the randomized algorithms that we covered in the homework. Alternatively, you can, so this solution, the running time of this solution is O of n squared, right? So you have 2 nested for loops. There are many solutions. There's an O n log n solution. You can think of this like, does sorting the vector help you find the most common element? There's an O of n solution that uses maps, which takes an extra O of n space. This is pretty good. There is also a solution which is linear as well, but does not use extra space. So it only uses a counter. It does not create another data structure. So this solution actually uses maps and creates another data structure. This solution, you can probably figure it out actually because the running time is n log n. And there are probably other solutions as well. But just, whichever one you can do will be the best. So that's for find most common. Let's scroll down. So the other problem that you are given is find peak of a mountain. So in general, you should read in detail what this statement is saying. Especially, you should focus on these parts, which are giving you some restrictions. But essentially what happens is, this is what you know. A mountain is at least 3 elements. If it's less, I ask you to throw an invalid argument error. Okay. Furthermore, a mountain always has a peak. A peak always has a single peak. So only one peak can exist. And a peak is an element that is greater than its neighbors. Okay. So what does that mean is that all mountains start by climbing up the hill. So you start going up where the numbers are strictly increasing, and then you start going down, climbing down the hill where the numbers are strictly decreasing. All mountains are of this form, and all mountains only have one single peak. In this case, the peak is 8, because the peak, this 8, is the only number in the array that is bigger than each of its neighbors. Okay? So there is a straightforward solution you can think of. So again, what I want you to do is that I want you to return, I forget if it's the index, let's see. Yes, I want you to return the index of the peak. Return the index of the peak. So what does that mean? For this example, we would want to return 0, 1, 2, 3, 4, 5. So if we call find peak with this array, we would want to return 5. That's what we want. So we can implement that. Find peak. Let's change the syntax to C++, so it looks a little better. Let me see, I think we can actually turn on comments. Okay, so now we have find peak, standard vector of integers. This is going to be my mountain. Okay, and hopefully you can see a straightforward solution here. I'll let you think about it for a second, but you can imagine, how do I find this 8 as the peak? Well, I climb the mountain, and as I'm climbing, I'm going up. And as soon as I start going down, which is here, then the number where I started to go down, like if the next number is smaller than me, so all of these numbers, if I look at the next one, they're going to be bigger. So 3 is bigger than 0, 4 is bigger than 3, 6 is bigger than 4, 7 is bigger than 6, 8 is bigger than 7. So I'm climbing up the mountain. And then as soon as I see that 7 is smaller than 8, then I actually know that 8 is my peak, given the restrictions that I've set up. So you can imagine a very simple O of n algorithm that essentially does that. So you would iterate over your input, mountain dot size -1 actually. So this -1 is important. You'll see why in a second. I++. And what I can do is I can say, well, let me look at my ith input. So let's say, let me look at mountain I. Are you bigger than mountain I+1? If you are bigger, right? So that only happens here. The first time it happens is here. I return I. Because the first time it happens, this will be 8, and this will be 7. So I can actually immediately return, I am done. Otherwise, I just keep going. If I ever get here, there was no peak, I would throw, I think it's this. This is the syntax, throw standard invalid argument. There was no peak. Okay, and this part I do want you to implement. I do want you to throw a standard invalid argument. So this is one possible implementation. Again, I will encourage you to consider, this implementation is pretty good. It's O of n running time, and it does not use extra space. So it is actually O of 1 space. There is an implementation that is O log n running time. And that one is a little bit more complicated to implement, but I encourage you to try it. After you have the basic implementation and you understand it, you can try the log_n implementation. It is a modified version of binary search. And again, with any modified version of my binary search, a couple of hints. Look at the middle of the array. Okay. Compare the middle to the neighbors. Okay. There are going to be 3 cases. You are either going uphill, so your left neighbor is smaller than your middle, which is smaller than your right neighbor, or you are going to be going downhill, which means your right neighbor is, your left neighbor is bigger than your middle, which is bigger than your right. Okay. For each of this, you should be able to get rid of half of the array. Okay. My battery's about to run out, so let's wrap this up. The last option is you are, your left is smaller than your middle, which is bigger than your right. And this is actually the easiest option because you just found your peak. You got lucky. You picked the peak. The middle is the peak. Again, there is a log_n solution that you can implement that is more complicated to code. I do not care which one you use, but feel free to implement whichever one you want. Okay, I will be ending the recording now. If you have any questions, come to office hours. Let's see, how do I...